innovation. Yeah, got it. Okay. I'm going to talk about the radical innovation and deep decarbonization, and also make the point that this should be profitable as well.
Professor, it seems that we are looking at a small window build order from your Mac.
Okay.
Can you please hide it or close it?
Yeah, sure.
So,
So let's see. We have to go where? We want to go back to your screen sharing. Okay, I'm going to stop share, and now let's try it again. This. Let's see. Desktop, Sadoway, Mexico City. All right. Now, if I go to this, is that okay?
there is still a small window on the right side of the screen.
Yeah.
I don't know why, and it's like on your Mac build order.
But do you want me to just get rid of that window?
Yes, and I don't know why. There is a small windows on the right side of your screen.
How's that?
It's gray. It says no build effects. Delay. It comes from your computer, I think.
See, now it doesn't want to allow me to change the slides.
Yeah, no problem. So I think we can continue. Just let's try to. Yeah, sorry for that. Yeah.
Okay, no, I have to do something different. We had it before, but now
Exactly.
now it's see it knows how to make a mess. Um, so what if I do this? That's not working.
No.
Okay, so now let's go back to this one here, this one here, and then this one here, share screen. This is the one, it's the Mexico City. Well, let's try this one. No, I think I don't want to touch this. Tell everybody that I'm sorry that I don't know how to run this stupid thing, but
No problem, Matt.
yeah.
Take your
Okay,
time.
share screen. All right, this is the one. This is my thing, Mexico City. All right. So now let's go to share. Okay.
Yes. Bef- Probably you should try to
Okay, I got it.
close. Okay, great.
This is okay. This is okay.
We still see this small build order window, but I think we can start.
So you don't see the whole screen.
Yeah, we see the whole screen, but there is a small window from the Mac, from your Mac software. It says build order, no build effects. Probably
Oh,
if you,
okay. I know what to do with that. Okay, I remember this one. All right, so I have to go to this and this.
yeah, on the bottom, I don't know if you can see this window. Yes, that one. Okay, that
Yeah.
one. Can
Okay.
you close that? Excellent. Great. Should work now.
Okay.
Excellent. Sorry. Thanks a lot.
It's good.
Yeah, perfect.
Okay. So I'm going to give you three vignettes. I'm going to go quickly. One is decarbonization of manufacturing, and that will be green steel and Boston Metal. And then one on the intermittency of renewables, that'll be stationary storage. So that'll be liquid metal battery, which leads to Ambri. And then finally, the aluminium sulfur battery, which leads to Avanti. So let's start with steel. So we know in 2019 that was 1.8 billion tons of steel made in the world. And that gives us 3.42 gigatons of CO2, and that was 9% of total CO2. Not 9% of total CO2 from the manufacturing sector. That was 9% of world CO2 came from steel, which is an astonishing amount of CO2. And so I started thinking about this back in the 1980s, and I knew that iron is found in nature as the oxide, either hematite or magnetite, and I knew that the electron can be a sustainable reducing agent instead of carbon, and so I put that with like dissolves like. We know that for aluminium, you put aluminium oxide into a fluoride, molten salt. But I said, well, why don't we put the oxide into an oxide? So I conceived of the molten oxide electrolysis, and that was the birth of this new technology. And so this would give us something that's a radical. It's not like aqueous electrolysis. We would have the decomposition of iron oxide to make oxygen as the byproduct instead of CO2. And this is what the cell looks like. You have the anode at the top here where the oxygen is coming off. This orange zone is the molten oxide electrolyte, which is a solvent. So you introduce iron oxide and it dissolves. And then by the action of electric current, we make oxygen bubbles here, and we make liquid iron at the bottom here, and it collects. So you see iron oxide goes into solution, we make liquid iron at the bottom, and we evolve oxygen gas at the top. And this turns out that it has a much lower capital cost than a blast furnace. And plus, you don't have to have coke ovens because there are no carbon. We don't need a sinter plant because everything dissolves. So it doesn't matter if you have big chunks of iron oxide or if you have fines, it will all dissolve. And you make pure iron, carbon-free iron, so you don't need a basic oxygen furnace. So you can see that the capital cost of producing iron is going to be much lower than it is in the current technology. And it turns out that this thing will scale at a much lower capacity. If you built an integrated steelworks today, you would need to go to, say, 2 million tons per year before it's profitable. And this thing here could work at, say, 100,000 tons per year and be profitable. So this is getting to the profitability argument. And of course, the whole thing was predicated on a commercially viable inert anode. So there came the discovery of the iron chromium alloy as an inert anode. And this is some examples. On the left here, you see this is the specimen. And in the middle, you see the specimen after 2.5 hours electrolysis. And it doesn't look so pretty, but it's because of the drag out of the molten oxide electrolyte. It's not because there's any corrosion of the cell. And this shows what's happening here, where you have a metallic alloy core and it forms a surface film of oxide which protects the alloy core and allows you to evolve oxygen. And this was published in Nature. And you know, Nature is the premier scientific journal on the planet. And when it comes to metallurgy, maybe once in 10 years do they publish a paper anything to do with metallurgy. So this was a big event for us. And my co-author was Antoine Alonor, who is now a professor at MIT, and Lan Yin, who is now a professor at Tsinghua University in Beijing. So this was a big event for career boosting for them. So we started a company in 2012 with Antoine Alonor and Jim Yurko and myself. And that company today is called Boston Metal. And we got the Series A funding from MIT Engine and Breakthrough Energy Ventures, and then some of these other people. And then the Series B funding from them, plus Fidelity, which is a big financial company in the United States, BHP, and Vale. BHP is in Australia and Vale is in Brazil. And together, these two companies represent 2/3 of the iron ore production in the world. So it's a big endorsement. And then even BMW has an investment arm, and they too are interested in green steel to put into their cars. So this is a 10,000 ampere cell. This was taken several years ago. They now have a 25,000 ampere cell, but this is, they're tapping This is while they're passing current, and you're going to see liquid iron come out at 1600 degrees Celsius, and the current continues to flow. So this is really scaling up. And so now, in summary, we have better metal. It's high quality metal, zero emissions, and much lower cost. I reject the notion of green premium. Green premium is code for technology doesn't work, it needs some special help, and so on. This would make metal for lower cost. And I think that the combination of these 3 points is a disruption. And this is the face of disruption. This is Amanda. She's a woman probably in her late 20s, and she works at Boston Metal. She wants to make steel. And this is the steel worker of the future. This is the way the industry is changing. Okay, so now let's shift gears and let's talk about electricity is tantamount to modernity. When you take a look at this image, and where you see light, you see the modern world. And when you don't see light, maybe maybe people don't live there, or maybe the place hasn't been electrified. So we want to electrify for everybody so they get access to the internet, to the wireless transmission, and so on and so forth. And so if you start looking where things are, then you ask, well, we want to make a sustainable electricity, and that means solar and wind, but they are intermittent. And so you have to have stationary storage at massive scale. Otherwise, the intermittent renewables don't make sense. And so what's taking so long if this is so important? And this is the issue. It's the specifications on stationary storage. You have to have long service lifetime, not 2 years, 5 years. We're talking 2 decades, minimum 20 years. And it has to be safe. You and a lithium-ion battery can catch fire. You can't have 100 megawatt-hour facility catching fire. And it has to be operationally flexible. It has to be able to give you long duration, constant current, and it has to give you short bursts of energy. And it also has to be able to absorb energy, because the way the grid operates, supply equals demand everywhere at all times. If supply exceeds demand, the quality of the electricity is bad. You get wrong voltage, wrong frequency. And so with the battery, you can quickly respond to current surges that can make the quality of the electricity unacceptable. And ultimately, this has to be super low price point. Nobody wants sustainable electricity at multiples of the cost of today's electricity. It has to be all of them. So this is a very difficult thing. So because cost was important, I changed the basis for research at the university and said we have to think about cost at the beginning. So I called it cost-informed discovery, meaning at the very early stages we think about cost. Most people think about cost later. They just invent a cool chemistry and publish in the journals and maybe form a company and say to the people in the company, it's your job to get the cost down. But I'm saying you have to bring that cost so low, you have to think about cost at the discovery phase at the university. And so when it comes for storage, this is what you need. I said, let's confine the chemistry to earth-abundant elements. And that means to make it dirt cheap, you should make it out of dirt. And you should make that dirt locally sourced so that you don't have the problems that we have today with lithium-ion batteries and the supply chain, getting the cobalt, the nickel, the manganese, the graphite, and so on. And also make it easy to manufacture, make it simple. And you think about all of this at the early discovery stage. And so you see here, I said, invent a colossal, cheap storage device. I didn't use the word battery, because if I say the word battery, you start thinking about something that looks like a 18650 or AA or something like that. So I said, if you pose the right question, then maybe you get the right answer. And the second thing is, in this field, I disregarded the experts. I did not speak to battery experts because these guys are very conservative. They're set in their ways, and they would tell me all of my ideas were crazy or everything's been tried, so don't even waste your time. So I didn't talk to the experts, and in addition, I looked outside the field for inspiration. You know, my other area of research was electrometallurgy, aluminum, magnesium, titanium, and so on. So here's an aluminium smelter, which gave me inspiration. This is one from Canada. This is probably 30 meters from left to right, and probably goes back about 2 kilometers. And this is 500,000 amperes, 4 volts continuously. So it's 2 gigawatts constant current consumption and making aluminium. And yet we can go from dirt to metal for less than $1 per kilogram. So I said, this is fantastic. If I can teach this thing how not to consume electricity, but to store electricity, and then give it back on demand, then I know I'm going to have something that's big and cheap, as opposed to starting with a battery that fits in your hand and try to imagine how to make it the size of this building. So it's a totally different approach. And this is the invention, a liquid metal battery. You see 3 layers. You see low density liquid metal, in this case magnesium, on the top layer. And the bottom layer is a high density liquid metal, in this case antimony. And in between was the molten salt as the electrolyte. And the molten metal is insoluble in the molten salt. And the molten salt is insoluble in the liquid metal. So the 3 lie on top of one another in the same way that you have, for example, salad oil and vinegar. So I don't need any membrane, no separator, and this thing is just self-organizing. And so what happens on discharge, the magnesium wants to go from the top to the bottom. But I just told you that magnesium metal is insoluble in the molten salt. But if magnesium becomes magnesium ion, then the magnesium ion can move from top to bottom. And to become magnesium ion, this thing loses 2 electrons, and the 2 electrons go through the external circuit, and they return to the antimony, where magnesium becomes a neutral, and now you make alloy on the bottom. So over time, the top layer grows thinner, and the bottom layer grows deeper. And that's how the cell discharges. And then to charge the battery, you force current through the cell, and that makes this into an electro-refining cell. So now the magnesium comes out of the antimony, goes across as magnesium ion, and then becomes magnesium metal on the top. And you restore the battery to its pristine initial condition. And as the electric current is passing, it generates heat, joule heat. And that's a threat for a lithium-ion battery. But here, we trap that heat. And so by generating heat on discharge and generating heat on charge, the battery runs without external heaters. So this is the idea behind it. And then we realized that this is a platform technology. We changed. I showed you magnesium and antimony, but we had other metals. So all of these metals are candidates for the top electrode. They're the most electropositive metals. So I showed you magnesium. We've worked with lithium, with sodium. Now we're working with calcium. These are all candidate metals. And likewise for the bottom, I showed you antimony. We've worked with lead. We've worked with bismuth. We could work with zinc. We can work with tin. So there's a plurality of choices for the bottom metal as well. And so then came startup time. 2 of my students came to me and said they wanted to form a company, and I said I was not interested in companies because I thought it was corrupting. And they said, listen, you want to talk about science and service to society? Well, this is your chance. Otherwise, you just publish a paper and the invention doesn't go anywhere. So Louis Ortiz and David Bradwell came to me and said, we're going to start the company, which was called the Liquid Metal Battery Corporation back in 2010. And then we changed the name subsequently to Ambri because we invented the battery in Cambridge. And so that's how I came up with the name Ambri. And the Series A funding came from Bill Gates. Bill Gates came to me. I didn't go to Bill Gates. He was watching my chemistry lectures online and wanted to meet me. And At that meeting, he said that if we started a company, he would be interested in putting money into it. And then the other first investor was the big French energy company Total. So that was the beginning. And then along the way, as I told you, we used lithium for one electrode and antimony lead for the other electrode, and that too resulted in a paper in Nature. And with that paper in Nature, it was powerful in launching the careers for many of these young people. And what was going on there was the main discovery was that the lithium antimony was a high voltage system, but antimony melts at 630 degrees Celsius. And we wanted to get the operating temperature down. And as you know, lead melts at 327 degrees Celsius. But lithium lead is a low voltage. So you can see in this graph here, I think I can show you in the next one. So this red curve is lithium lead. And this blue curve at the top is lithium antimony. So if we added lead to antimony, the melting point would come down. But we figured that the voltage would come down as well. There would be somewhere in between. And I said, well, let's see what it's like. You know, maybe it's, you get a substantial decrease in operating temperature with a modest decrease in voltage. This was the surprise. The voltage stayed high. The voltage stayed high because when the lithium went into the antimony lead, it reacted preferentially with the antimony. And so we got the low melting eutectic temperature for operating, and yet the high voltage of antimony. And that was the discovery that warranted the Nature paper. And this is my group in the summer of 2011. There's 20 people in this image. And of the 20 people, there's myself, there's Luis Ortiz, and David Bradwell. And they were the only ones that really knew the molten salt chemistry and the liquid metals. And then we had all these other people that came. They were very bright, but they were actually at some level newcomers to the field. And as a result, we had the ability to invent things because these people were fearless, intellectually fearless, and they did things that any battery guy wouldn't do. So that's the story. So today, right now, Ambri is making calcium antimony, and you can see over time it retains 99+% of nameplate capacity. So it's very much fade resistant. So Ambri's 12 years old, I'm sorry to say, but this is tough tech. It's not like writing code. And anybody who thinks you're going to start a new battery chemistry and in 6 months you're into market, that's not the way it works. This is very, very difficult. We had many, many obstacles to master how to manufacture at scale. And it was just announced last month that Microsoft is going to be the first customer to use the Ambri battery to go along with their solar powered big data centers. And so now Ambri is expanding their manufacturing facilities. They're just outside of Boston here, about 45 kilometers to the west of Boston. Right now they're in Marlborough, and they're moving into larger facility in Milford. And once Microsoft announced that they were buying, and you know, this is funny because if you look at these big facilities with lithium-ion batteries, they're all government sponsored. No power company is spending real money on this, but Microsoft is spending real money on this, and now everybody's calling Ambri to get into the queue to be ordering the liquid metal battery, and their order book now exceeds $500 million. That's why they have to build the facilities. They weren't going to build the facilities if nobody was going to buy the battery. So it's a chicken and egg situation, which again explains why everything moves so slowly in this sector. And included in that $500 million order book is a joint venture with Reliance Industries in India, where Reliance is going to take a license on the technology and manufacture the liquid metal battery in India for the Indian market. And then I chose another problem, and people were asking me, could you use the liquid metal battery, say, for a single family home? And I said no. What we learned from Ambry is that the liquid metal battery really needs to be large. It needs to be tens of megawatt hours, preferably 100 megawatt hours and up, because then it generates enough heat. If it gets too small, the heat loss is faster than the heat generation. So if you think about a single family home, it doesn't need tens of megawatt hour storage. It needs something more like what you see in an electric vehicle. See, something like 100 kilowatt hours. So I said, let's start thinking about that market. And people say, well, you can use lithium ion, but it's still too expensive. It's unsafe. In many jurisdictions, fire marshal will not allow you to put 100 kilowatt hours of lithium ion battery in your home. And you know how lithium ion battery loses capacity. So, okay, let's say you have a 10-year-old lithium ion battery. It's not putting out 99% of the nameplate capacity. By then it's probably down to about 80%, which means it will not give you all the energy that you need. So either you add new cells or you oversize it on day one so that you are already ahead of the capacity fade. So even if it loses 20% capacity, you will still have enough to meet your needs. So again, I went back to the cost-informed discovery, and I looked at the periodic table, and I said, well, what's the most abundant metal in the Earth's crust? And that's aluminium. And what's the most abundant non-metal? Well, that's sulfur. And so I said, that's going to be my bookends, and that's how I'm going to make the next chemistry. So I said, we put aluminium for the negative electrode and sulfur for the positive electrode. Now, what's the electrolyte? It can't be aqueous. And I don't want to use the volatile, flammable electrolyte that's used in lithium-ion batteries. And we found low-melting molten salts. I'm talking about low-melting molten salts that are operable even below 100 degrees Celsius. So that's going to be totally acceptable in the home. It cannot catch fire and very cheap. And so the capital cost of the active components, that's the aluminium and the sulfur, it's less than $3 per kilowatt hour, which is 5% of the capital cost of the lithium ion components. And it's completely sourced in North America. We can do everything with resources in Mexico, in Canada, and the United States. No China, no Congo. And even the brines that are used out of Atacama Desert in Chile, they end up going to China to be processed into the compounds that are needed for the lithium-ion battery. So this is a big problem with the world supply chain. Whereas this can be done, so aluminium sulfur can be made 100% in North America. And so we started the work at MIT starting around 2014, 2015, and found something that works. And this is an example of the battery. You have an aluminium metal electrode, which is the negative, and the elemental sulfur, which is the positive. And sulfur, as you know, is an insulator, electrical insulator. So we have to pepper the sulfur with some conductive carbon, and then in between as I told you, there's a molten salt electrolyte, and then we put in a polymer separator. In this case, we're using just simple fiberglass so that you can press the electrodes together without shorting. And then on the back side of the positive electrode, we use aluminium as the current collector. So aluminium is the active member of the negative electrode, and it's also the backing for the current collector on the positive electrode. And then if we put the polymer insulator on the back of the aluminium current collector, then we can roll this up into a wound version, jelly roll, what have you. And so this was published in Nature in August of this year. 24th of August it appeared online. And, again, for me, I don't care. I don't need the publications. But for all of these people here, this publication was a huge career booster. And it says aluminium chalcogen because we did experiments both with aluminium sulfur, and we also did experiments with aluminium selenium. Now, I know selenium is expensive and so on, but it's group 6 member, just as sulfur is. But it was like a placeholder for sulfur because, as I told you, we had to put carbon in the sulfur and so on. Whereas selenium is a metal. It's an electronic conductor. So it gave us sort of sulfur-like chemical performance, but it gave us electronic conductivity. So I said that the aluminium selenium was more like a training wheels for the aluminium sulfur. And then we also filed for patent, and that patent was issued in March of this year. And of course, MIT owns the patent. And then I formed a company called Avanti, and with Luis Ortiz, and then we took a license from MIT, and we're now out in Watertown starting to build. And this is after only 5 months. So in my right hand here, I'm holding the aluminium sulfur battery in the pouch cell format. You can see there's a aluminium tab and a copper tab. And then here is the same thing, but it's in a wound version. So, I mean, these are several amp hours. So they're almost starting to approximate the battery that powers your mobile phone. And then the last thing is I started one more company. It's called Sadoway Labs Foundation. And I wanted to have what I call a skunk works, so that I would have a laboratory to be able to conduct experiments in for radical ideas. Because I was leaving MIT and I wanted to have a lab, because I don't have a lab now at MIT. So this was very hard to raise funding because it was last year during COVID. But we managed to get support from Schmidt Futures. Eric Schmidt was the CEO of Google for many years. And he and his wife started this foundation called Schmidt Futures. They want to fund the unfundable, and they decided to fund me. And so what they're interested in is technology for climate change mitigation, and that's what I was able to persuade them about. And what's unique about the Sadoway approach is I call it extreme electrochemistry. What is extreme electrochemistry? It's non-aqueous electrochemistry. I don't do anything in water. And so there are two major classes of liquids for non-aqueous electrochemistry. As I've already shown you, there's molten salts, and they go to high temperature. You can start at, say, body temperature, 40 degrees Celsius, and go up to 2000 Celsius. So there's the molten oxide electrolysis and so on. All of that is in there. And then there's another class of liquids called molecular liquids, things like thionyl chloride, DMSO, and so on. And so that takes us into low temperature, from as high as 190 degrees Celsius down to minus 100 degrees Celsius. And there are advantages in materials processing and even in battery electrochemistry there. So what's the product? What if this is a foundation, because it's a foundation, it can't be for profit. So what are the products? The new technologies will come out of Sadoway Labs, and then that will spin out new companies. So that's what's going on there. And there's also educational, where people can come to Sadoway Labs as postdocs. And after they've spent a year or two at Sadoway Labs, they will leave with their eyes open. And so I say that this is a place for inventing inventors. So I think I'm going to bring this to a close and say that I'm going to predict an electric future, and almost all industrial chemistry will become industrial electrochemistry. If anything can be done electrochemically, it will be done electrochemically. And if it can't be done electrochemically and still needs thermal chemistry, then instead of burning gas, we'll use electrical heating to do that. So I think it's a bright future in electrochemistry, and I think that this is an example of where you can cross science and service to society with profitable sustainability. So I think this is a good place to stop, and I'm happy to take questions.
Yes, great. Thank you very much for this very nice presentation. As you said, we have enough time for questions, so feel free to ask or to write questions on the chat also. Yes, Professor Ramos, please go ahead.
Thank you very much for a very, very interesting presentation, very inspiring. My question concerns the system that you called AMBI battery, which in my understanding is the one that has the largest capacity. And the question is, has it been tested or thought about for applications with wind energy? Wind energy has its own peculiarities and needs energy storage. So I wonder if you have given a thought about this kind of application.
Yes, wind is definitely an application because, as you point out, wind just as solar, they're both intermittent. And so when the wind doesn't blow, we need to have some other source of electricity to bridge that gap in generation. And so people who are proponents of wind generation are in that order book looking to adopt AMBI batteries to make, as they say, to firm up the generation of electricity by wind.
Can I just make a quick
Yes.
addition to my question? I also was wondering, how long does it take for these large capacity batteries to charge and discharge? How fast can you do this cycling?
So on the charge, it's capable of taking very high surges. So you could easily charge this thing in a matter of hours. 3-4 hours could easily charge. So if you imagine you're with solar, say in the highest intensity of sun in the middle of the day. And then for discharge, oddly enough, people don't want rapid discharge. They want to have a long duration discharge, maybe 8 or 10 hours. But this could be, if you're willing to go at lower rates, it could go probably as long as 12 hours. But if you go too slow, you won't generate enough heat. So, it's really designed to be used every day. So you charge it every day and you discharge it every night. It'll be fine. Now, with wind, of course, the wind is different. The wind may not be blowing. Maybe it's blowing at night and it's not blowing in the day. So again, it's for some fraction of day. That's where it works really, really well. But also, if you have what they call this ancillary services for frequency regulation, where maybe for 15 minutes you need to take current surges and clip the peaks off of those current surges coming into the grid, the liquid metal battery can handle those current surges.
Yeah, thank you very much.
Yeah, thank you. Any more questions from the audience or in the chat? I have one. How many cycles can these batteries from Ambri can handle? I mean, in term when compared to the lithium-ion batteries.
So we have data. I didn't show it in the talk, but I showed you just a little bit of calcium antimony. But we have data from other systems. So this is across the different chemistries. There were some cells that were running for almost 5 years and deep discharge every day and get up to 5,000 cycles and still retaining over 99% of nameplate capacity. So we're confident that when we're making representations to prospective buyers that we would put service lifetime of 20 years. And you know, this is not like the old incandescent light bulb where one day it's shining, it always shines brightly, and then one day it breaks and it doesn't shine at all. This is more like what you experience in your phone or your laptop. It doesn't fail. It just runs less well, and every day it runs less and less and less time until finally you say this is unacceptable, and then you want to get a new battery or a new phone. And so the same thing with a liquid metal battery. We say it's going to run for 20 years. We mean that after 20 years it's still giving you over 99% of the nameplate capacity, because the lithium ion battery, in principle, you could keep it running for 20 years, but as you start approaching 20 years, it's not going to give you the nameplate capacity. It's going to be probably below 50% of nameplate capacity, which means you're going to have to spend more money to make that shortfall, or in anticipation of the shortfall on day one, if you need, say, 100 megawatt hours, you will install 200 megawatt hours so that in 20 years' time you can still have the 100 megawatt hours.
Right. Thank you. Professor Cuevas also raised his hand. Sergio.
Thank you, Alberto. Thank you very much, Professor Sadoway, for the very nice talk and interesting. I would like to ask, what do you think is the main obstacle to spread the technology in a rather short time? So do you think it's mainly, the main obstacle comes mainly from financial aspects, or I would like to know your opinion about this, please.
So my opinion, based on experience, is that massive stationary storage is so new and so different that the people who are looking to buy this are very conservative. They're concerned about making the wrong decision. And I like to say, if you go into a capital-intensive, risk-averse market, then nobody wants to be first. They're all afraid that they're going to make the wrong choice. But everyone wants to be first to be second. So with Microsoft having the courage to choose the liquid metal battery, now others are starting to say, if Microsoft is doing this, maybe it's okay if we do it. Because there's this, so there's two problems. As I said, one is the risk aversion. They're concerned. I mean, is Ambri even going to be around in 20 years' time? All of this kind of stuff about the risk. And then the second one is the distraction of lithium ion. Lithium ion works, but it's still far too expensive and it's far too dangerous, but it works. You see this with automobiles. I mean, lithium ion is not the correct chemistry for the electric vehicle, but it exists. And if you know the car companies, these guys are very conservative, and they have no patience to fund research. So they will go with whatever is available. And so with that as the sort of the landscape, if I show up with a new battery, they just look at it and say, well, you say it works for 20 years. Do you have 20 years of data? And I'm saying, you want me to give you 20 years of data? Okay, so I guess we're going to just do nothing for the next 20 years until I can demonstrate that it lasts 20 years. So the bar, the expectations are so high that it's almost self-defeating. They're almost looking for a reason not to adopt. But as there is more and more intermittent renewables going onto the grid, wind and solar, the grid can accommodate intermittency from wind and solar when it's down around 5% of total generation. But when wind and solar start getting up, say, to 20%, the grid is going to have big trouble. You cannot run that grid with big gaps, intermittency, power surges, so on. It's going to be terrible. So they have to get something in stationary storage. But they want radical innovation and zero risk. And of course, those two are orthogonal. They don't come together. So that's why things are so slow.
Thank you very much.
Mm.
Sorry, there is one question on the chat from Aruna Chalam. She said, thank you very much, Professor Sadoway. I had a question on the electrolyte. What is your opinion on using ionic liquids instead of molten salts for the aluminum sulfur battery?
Yeah, we did some testing with ionic liquids, but we found that the conductivity of the ionic liquid is much lower than the conductivity with the molten salt. And also, surprisingly, the electrode kinetics are slower in the ionic liquid. And finally, as you know, the cost of ionic liquids is pretty high. I mean, ionic liquids are fantastic as reaction media, but when it comes to electrochemistry, when you go to very, very cathodic potentials, say for aluminium, lithium, and magnesium, and so on, the ionic liquid is a little bit unstable. The big cations can be weakened. So yes, we did think about it, but we found that the chloroaluminates, and it's all written up in the paper, the chloroaluminates are far superior and much cheaper. So I mean, we did look at them, but we favored the molten salt.
Nice.
Thank you, professors.
Thanks. Can you say something about the sodium electrochemistry? There are some recent publications from the European community about this technology. What do you think?
So there's two things. I mean, the whole business of trying to go beyond lithium ion with sodium ion, I think that's an avenue worth traveling down. Personally, I've not been working in that, but it does make sense because it has many of the similar characteristics as lithium ion, and as you know, sodium is much cheaper and much more earth abundant than lithium. So, but I don't have a direct experience with that. Now, we did work with sodium in molten salt, and so one of our early liquid metal batteries was sodium bismuth. So we had sodium as the negative electrode floating on the top, and the electrolyte obviously had sodium ions in it, so it was sodium chloride with, say, potassium chloride and what have you, and bismuth on the bottom. And it ran for many months. However, it may come as a surprise. So I did say that say magnesium is insoluble in the molten salt, and molten salt is insoluble in the antimony, and that's correct. But sodium has this peculiar property in that sodium is sparingly soluble in sodium chloride. And so when sodium metal dissolves in sodium chloride, you get sodium ions and solvated electrons. And so the sodium chloride becomes somewhat electronically conductive. And why that's important is that when you fully charge the battery and you've stopped passing current and you're just letting the battery sit there, and then some hours later you're going to draw current from the battery. While the battery is sitting there, because the electrolyte has some electronic conductivity, there will be what they call a discharge, self-discharge current. And what it means is that you charge the battery to 100%, and 4 or 5 hours later you've lost, say, 15-20% of your stored energy because it's leaking. It's a leakage current. And so this is why the liquid sodium doesn't appear in liquid metal batteries. Now, if you look at sodium sulfur or sodium nickel chloride, which is known as zebra, both of those have liquid sodium, but the liquid sodium is contained in beta alumina, like a U-shaped tube of beta alumina. And the beta alumina blocks electronic conductivity, allows only sodium ion conductivity, and so both of those battery chemistries will hold charge. But when it comes to just liquid metal battery, sodium is problematic for self-discharge, leakage current.
Thank you. There is one question on the chat. Thank you very much from Christian Ramos Ruiz. Professor Sadoway, is there any kind of waste management?
Yeah, so the liquid metal battery is actually quite good in that respect, because let's say after 20 years we decide, just out of caution, the battery is still operating, but it's got steel housing and so on. Maybe we want to be safe, so we will shut the battery down. So the steel of the housing can obviously go to electric arc furnace, remelting, and so on. And then let's say we have, right now we have calcium chloride, and antimony. Well, all of the components of that battery are still useful. The salt can be recycled, and both of the metals can be recycled. I showed you that when you charge the battery, you are essentially running an electro-refining cell, which is how you purify the metal. So there isn't a landfill disposal problem or anything like that. We're not using huge quantities of water. So I think when it comes to end of life, liquid metal battery gets a very high rating.
Thank you. Any more questions from the audience? Okay, well, I think that if there are no more questions, I will kindly ask you to please join me to thank Professor Sadoway for this very nice presentation. Yeah, thank you very much, Professor. It is really a pleasure to have you with us today, and we really enjoy your talk.
Yeah, my pleasure to be here, and I was really excited to see not only the people from Mexico City, but people coming in from Europe and from Asia. I mean, I had no idea that you had such a global reach, so congratulations.
Yeah, thank you very much. As you said, yeah, this is a transcontinental meeting, and we are lucky for having you today, and all our colleagues for joining us also. Well, thank you very much.
Okay, you're welcome. We'll see you.
We see you.
Be well.
Thank you.
Be well. Take care. Have a nice day.
Bye.
Bye.